Okay, hi guys, it's Ms. Gemma again, and today we are doing the work, energy, and power topic. So hopefully by the end of this lesson, you will be able to define work and energy, be able to explain the work energy theorem, and then calculate various values based on work, net force, and the work energy theorem. Okay, so as always, I'm quickly going to go and use my whiteboard to explain all the theory, and then we'll go through the PowerPoint. So I've written on my whiteboard, because I'm pretty sure you didn't want to see my handwriting for this, how you can phrase what work is and how you can phrase what energy is. So work in layman's terms is basically just the amount of energy that you give or take from an object. And work is energy being transferred by a force of some kind. And so it is an action done on an object whereby it causes displacement of that object. And energy, on the other hand, is the ability to apply a force, or it is the ability to do work. And so what we can then do is we can put this concept together. So if we go like this, we can kind of get a little formula from it. And we can say that work is basically a force times distance. And when we say that, what we mean is that if you have an object, let's say I've got a box and it is on a surface, and I push this box with 10 newtons, and I push it from this point to that point over a 7-meter distance, then I will get to the point where I can say work is basically just equal to that 10 newtons times the 7 meters. So it is 70 Newton meters. And Newton meters is actually the unit joule, which is the unit for energy. So work is basically energy, but it is energy being done or being transferred because of this force that is applied to an object. So how we then go and define it is we can say that work is equal to force times the change in distance times the cosine of the angle theta. And the reason that we put this bit into the formula is because if I have this same box, but now I am pushing it at an angle. So same box, but now I push it, let's say, from the bottom upwards, okay, at 10 newtons. We can't use that as the force being applied, because as we have learned in grade 11, you have an x component and you have a y component. And the only component that allows this box to move is your x component. And that is found by multiplying the force times the cosine of theta, if this is my angle theta. And that is just normal trigonometry. So if you have a triangle, okay, and this is your angle theta, and you have this value over here. So oops, I made a mistake, sorry. So toa, then cosine is equal to the adjacent corner, which is this, and over your hypotenuse. And that is why we use cos. Okay, and so your F in this case is just the size of your force. Your distance is always measured in meters, and it's the change in the distance, so how far it's traveled from the start. and your cos is the angle at which the force is being applied. Okay, but now, like I was saying in this one definition, the work is actually just the amount of energy that you are giving or taking from an object. So if you want to find the net work, then you could use the formula work net is equal to work 1 plus work 2 plus work 3 up to n. So it is basically just adding all of your work together. But this isn't always possible to work out. So what we end up doing is we take Newton's laws and we kind of apply it into this, and we say, what if we say that the net work is equal to the net force times the change in your distance. And now, hopefully you remember from grade 11 that F net is equal to mass times acceleration, okay? And so if I go, I just want to make some space over here, okay? If I go and I say, let's substitute this bit into this formula, we can rewrite it as the net work is equal to mass times acceleration times the change in distance. But using our grade 10 formulas for velocity, we can write acceleration in terms of velocity. So if we use the formula, final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in distance. We can now go and rearrange this formula so that A is what we find. So we'll subtract your initial velocity from your final velocity, and then we will divide that by 2 and the change in distance. Then I'm going to take this and substitute it into my equation here. So I'm going to say mass times final velocity squared minus initial velocity squared divided by 2 times the change in distance, and multiply that by the change in distance. These two can cancel out, and I am left with a half times mass times final velocity minus initial velocity. And if you look at this formula, what does that actually represent? Does anyone have an idea? I will go and actually multiply out my brackets. Maybe that rings a bit of a bell. So this can become half mass times Vf squared minus half mass times Vi squared. Any ideas what that looks like? What type of energy? No one? Yes, Monica, it is kinetic energy. So hopefully this shows you that this is actually saying that the net work is your final kinetic energy minus your initial kinetic energy. So net work is actually just the change in your kinetic energy. Okay, and that is how we get to the work energy theorem. So what they did is they basically went and they said, well, work is the amount of distance that an object travels when a force is applied to it. And we know that a net force is due to mass times acceleration. So if we substitute those equations into our work formula, we can actually find that net work is actually just the change in the kinetic energy. And then if you want to take it a step further, you can go and say, well, how do we measure the rate at which something does work? So let's say we've got two guys, bodybuilders, and they're standing in the gym and they are busy lifting weights. So they're doing deadlifts. And the one guy, let's say his arms are really long and he's holding that above his head. And the other guy, and so this guy over here can pick up the weights in, let's say, 2 seconds, and this guy over here can only pick up the weights in 6 seconds. But they're picking up the exact same mass and they're using the exact same amount of energy. So what's the difference? Well, we say that they have different power. So power is equal to work divided by the change in time. So if we look at this example, let's say they are applying 5,000 joules to pick up those weights. Okay, then for this person, let's say this is person number 1, he will have a power of 5,000 joules divided by 2, which is equal to 2,500 watts. And the second person is equal to work divided by change in time is equal to 5,000 divided by 6. And that is equal to 833.33 repetitively. So do you see that even though they're using the same amount of energy to lift these weights, they are doing it at a different rate. And because they're doing it at a different rate, they're using less or more power. So person number 1 doing it so quickly is using more power than the guy doing it slower. So power is basically the change in work over time. So it's the rate at which work is being done. And you can also go and we can say, well, let's say power is equal to work over change in time. And we want to substitute the formula for work in there. So F times delta X cosine of theta and divided by the change in time. And let's say that these are all horizontal forces, okay? So we don't have to worry about the angle. So for argument's sake, we take away the cosine of theta and we say it's just equal to force times the change in distance over the change in time. Well, change in distance over change in time is equal to velocity. So you can actually say that power is equal to force times velocity. So you can go and write work in terms of velocity, but you can also go and write power in terms of velocity. And this formula over here is normally used for what we call instantaneous velocity. So if they tell you a car goes from 0 to 100 in 5 seconds, and you want to know what is its power at 100 meters per second, you can use this formula if they give you the force at which it moves. So this is basically what work is and what power is. And one thing that I didn't mention, because you're probably wondering, well, where does potential energy come in to this? And I'm quickly just going to explain that. So just remember, if you have a situation where we're not working with a horizontal force, but we're working with something going up and down. So let's say you have a ball on the ground, okay, and you are going to lift it to a distance h, okay, and we say that force is equal to, that work is equal to force times distance, change in distance, and this time it's going to be, my distance is going to be h, so it's going to be force times h, and we also know that F is equal to ma, because there's no other forcing acting on this object, so this is going to be ma times h, but because you're working vertically, this acceleration has to be gravity. So remember, when you are dropping something from height or you are throwing something up vertically, we always use gravitational acceleration, so 9.8 meters per second squared. So then your formula for work will become mass times acceleration, which is gravity, times height, and this is potential energy. So if you're working with an object moving up or down, then we say that you are working with potential energy. If you're working with an object moving right to left, then you are working with normal m times a, whatever your acceleration is, and you can substitute in velocity if you don't have acceleration. So let's go to the slides and just relook at those definitions and formulas, and then we will do an example. Okay, so the first one, the proper definition for work, which you have to write in your final exams, is when a force acts in or against the direction of motion of an object, work is done on the object. Okay, very important here, work is a scalar quantity, meaning that you can either have a positive or a negative amount, okay? You don't have to indicate direction. It is not a vector, it is a scalar quantity. And your formula is work is equal to force times the change in distance times the cosine of theta. Like I was saying, work is measured in joules, force is measured in newtons, your change in distance will always be meters, and theta is the angle between force and the displacement. So if you don't have a linear displacement, a horizontal displacement, but it's being done at an angle, so they're pushing downwards or they're pushing upwards from some random angle, then you will use cosine of theta. Okay. Then, like I was saying, work is a scalar quantity, meaning it can either be positive or negative. When you have a positive value, you are saying that the object is gaining kinetic energy. So you're basically saying that your object is speeding up, okay? If you have a negative value, it means that your object is slowing down. So you're losing kinetic energy. So think about it in terms of throwing a ball and catching a ball. When you throw a ball, okay, you're pushing it away from you, you're giving it energy, it's moving. When you catch the ball, you are taking that thing that is moving, catching it in your hand and slowing it down so that it comes down to 0 meters per second or to rest. So you are moving against the object. So you're decreasing its kinetic energy. If work is equal to 0, it just means that there is no change in your kinetic energy, which means that your object is moving at a constant speed. So it's not slowing down, it's not speeding up, it's just moving at the speed that it was moving originally. It's cruising. Then your work energy theorem, like I was showing you how we get to the whole formula, I've never ever seen them ask you to prove it, so you don't have to worry about proving it. I just wanted to show you why we get to where we get. And the work energy theorem states that the work done on an object by the net force is equal to the change in the kinetic energy. Very important, this is only for a net force, okay? Please don't apply this rule if you're not working with a net force. And so it would be your final kinetic energy minus your initial kinetic energy. Then you get two types of forces. You get a conservative and a non-conservative force. So a conservative force is one in which work done by or against it depends only on the starting and ending point of a motion and not on the path taken. Another way of phrasing it is, a conservative force is where your system doesn't lose any energy in the form of heat or sound or anything like that. So the best example of a conservative force is something like a pendulum. So your pendulum will move from side to side and it would never lose any of its energy. You will go from having kinetic energy at the top and then it comes back down to the bottom and then it goes up for potential energy, it comes back to kinetic energy, it goes to potential energy, kinetic energy, and it just keeps doing this little dance. Have you all copied down conservative force? And so the formula that they use for conservative force is that it is the negative of your potential energy. Then a non-conservative force is one in which the work done on the object depends on the path taken by the object. So for these type of forces, they tend to lose energy in terms of heat and sound. And so the formula would be you would take both kinetic energy and potential energy into consideration. These are normally your real life situations. And so your force doesn't necessarily have to be horizontal, and these will always generally be your forces that are at an angle. But don't worry, we're going to do an example and it will all make sense. Okay, can I move on? Yes, Mfilo, you can. Conservative force is more a whole system though. It's not just one specific thing. It is a whole system that's occurring. Because remember, yeah, you're right. If you're talking about force specifically, it will be gravity. Then power is defined as the rate at which work is done or the rate at which energy is transferred to or from a system. And like I was saying, power is equal to work divided by time. And then you can substitute force times change in distance times the cosine of theta into that formula if you don't have the work value yet. So here's an example from the November 2018 paper 1. I have this on my whiteboard, so I'm just going to go to this question quick. Okay, so question 5, they say in the diagram below, not drawn to scale, shows a vehicle with a mass of 1,500 kilograms starting from rest at point A at the bottom of a rough incline. Point B is 200 meters vertically above the horizontal. Then they tell you the total work done by force F that moves the vehicle from point A to point B in 90 seconds is 4,8 times 10 to the 6 joules. Then question 5.1 asks us to define the term non-conservative force. So we can just say a non-conservative force is if the work it does on an object moving between 2 points depends on the path taken. Okay, and so that is question 5.1. Question 5.2, they say, is force F a conservative force? Choose from yes or no. So do you think it is a conservative force? No. No, it isn't a conservative force. So your answer there would just be, I'm just going to highlight it, no. Then they ask 5.3, calculate the average power generated by force F. So we use our formula. P is equal to work divided by change in time, which is equal to this value over here, 4.80 times 10 to the 6 joules, divided by this time, 90 seconds. That gives me an answer of 53,333.33. Okay, and always try and write it in scientific notation. So I get 5.33 times 10 to the 4 watts. Or you could have said it is 53.33 kilowatts. Your choice. Just remember your unit of power is watts, which is very important because if you don't use the right unit, they do have the ability to take away points. Okay, then the speed of the vehicle when it reaches point B is 25 meters per second. Okay, and they tell us in 5.4 to state the work energy theorem in words. So 5.4 says the total work done on an object is equal to the change in kinetic energy. So you're basically just stating that if the work net is equal to change in EK, you're just changing that to words. Then they ask us in question 5.5, use energy principles to calculate the total work done on the vehicle by the frictional forces. So 3 things is happening in here. Okay. The first thing is you have force F, okay, that is moving this car up this hill. You have your frictional force from this rough surface that is trying to push it back. That's your frictional force. And you're also going to have, when it gets here to B, you're going to have your normal mg, okay, your weight that plays into it. So when we work out F work net, we actually now have to take all of that into consideration. So work net is equal to the change in kinetic energy. And the reason I'm using change in kinetic energy is over here, they gave us 25 meters per second, which tells me that I'm going to have to do something with velocity. So what I'm going to do is I'm just going to write this out and say it's a half times mass times Vf squared minus Vi squared. And then on the other side, I'm going to add up my different work that is being done. So we are doing the potential energy work, which is just going to be our weight over here at the top, but it is at a different angle because you're going in the opposite direction of what's normally positive and negative. We're going to have our frictional force that is going to give work, and we are going to have our force F that is going to cause work. So then to get this over here, we are going to say it is M times G times change in distance times the cosine of theta plus WF is what we're trying to work out, our frictional forces, the work done by them. And then this value over here is given to us as 4.8 times 10 to the 6. On the other side, you've got a half times the mass. And they told us that our mass of our car, it's cut off here, but it's in there, is 1,500. And then your final velocity is 25 squared minus 0 squared because you started off over here at rest, which they tell you there in the story, 0.8. So it's very important to read all your information. And then I put this into my calculator and I get a value of 468,750. Okay, I am going to leave this as that because I have nothing to add it to yet. I'm going to leave work of friction. And then I'm going to put my values in here and I just want to make some space. Sorry. There we go. Okay. So once again, my mass is 1,500. My gravity is 9.8. My change in distance comes from over here in my picture. So I'm at point B. Oops, wrong. So it is going to be this 200 meters. That is my change in distance. And my angle theta, and this is really important, is going to be 180 degrees. The reason being that you are moving upwards. And remember that gravity is positive when it goes down. So we put in this because that just makes your amount negative. If you were to use it in terms of direction from the start, working out your force correctly, that is also fine. I'm just not working it out in terms of force, I'm working it out in terms of work. So it is times 200, which is my change in distance, times the cosine of 180 degrees. Okay, if I put this into my calculator, I get a value of 294 with 4 zeros. And I hope someone is doing this with me and double checking. Plus 4.8 times 10 to the 6 is equal to 468,750. Okay, then I'm just going to add my like terms. So work of friction If I add these two together, I get a positive amount of 1860000. Now I will take it to the other side, so I'm going to subtract. And so my work from friction is negative 1391250. And then always just try and write it in scientific notation. It just makes it easier to write it. Negative 1.39 times 10 to the 6 joules. Okay, always remember your unit. Very important, remember to keep it negative because of the fact that it is a scalar quantity. So has someone been double checking my maths? Was all my answers correct? Do you all understand where we were getting our values from and why we were using the values that we were using? Does the work energy theorem make a bit more sense today after this? I was thinking you guys are going to have a lot more questions. The object isn't speeding down, it's slowing down, yes. So it's decreasing speed, which makes sense because as you go up a hill, you either need to put in more work, you know, at a bigger force, or you're going to slow down because you're having a lot more resistance as you go up a hill. So yes, because you have a negative answer, it means the object is losing energy, so it's basically slowing down. Okay, so that was it for today. I actually thought you guys were going to have a lot more questions. You made it seem like you were stressing about this section. Tomorrow, I'm just going to work through 2017, 2016, and probably 2015's past paper on this. Just show you how to answer them, where to find what is in the paragraphs, what isn't. And then, yeah, we'll see what we do on Friday. Is there any questions? Are you all good? No, this one is friction. The one that we were trying to work out is frictional force. This one, this little f. Sometimes they do like this little thingy. That is, this is for your force coming from the fact that you're standing on top of a hill, so you've gone from 0 to something. How do you determine theta? Oh, okay, so the reason we used 180 over here is because we are moving up the hill, so we are going in the opposite direction of gravity. So that's why it would be cos 180. So remember in forces, you also use that if you were using a frictional force, then you would use cos 180 because you're going in the opposite direction. So this is the same concept. If you were to work the force out before you worked out the work, in this case, you would have just put in the negative 9.8 meters per second and then go from there. But because this is a scalar quantity, you can't indicate direction in that way. So you have to use theta. Does that make sense, Ms. A4? Okay. Okay. So so if it was going in the same direction, you could have just neglected to use. You would have had an answer of 1, so it would have been cosine of 0. If it's cosine of 90, then you have your answer 0. If it's cosine of 0, oh, let me just put that on the side. So cos of 90 degrees is equal to 0, and cos of 0 degrees is equal to 1. because your graph looks like this. It goes like that. So at 0, you've got 1. At 180, you have -1. Oh, that's 1, sorry. You've got -1. And then there at 360 again, you've got +1. But at 90, and this is 270, I think, you would have 0. Yeah, so it would be cosine of 0 if you were going in the same direction. Okay, so like I said, tomorrow we'll do 2016, 2017, and 2015's papers. See you guys tomorrow, same time, same place. Have a great day. Oh, just before I go, just quickly go to the slides, and I just want to show you here are some really good links on the slides, so please go and check them out. If you're not 100% sure with the theory or whatever, they're really good to use. Okay, see you guys tomorrow.